without hopefully much further ado, we will turn it over to Paula to learn about insights from the USDA Forest Service plantation monitoring data. You can see everything now, right, Paula?
Yep, I can see everything. And so to keep the ball rolling, let's just move on to the next slide.
Yep.
Okay, so national forests in the West follow a relatively standardized protocol when they monitor post-fire plantations. So the first thing that they do is they go out and they permanently mark a subset of planted seedlings in a subset of the units. And these can be either along stake rows, which are basically transects, or they can be marked in plots. They then track seedling survival always for one growing season after planting, usually after 3 and sometimes also after 5. They then report the survival rate into facts by unit and species. In addition, just for their own information needs, they sometimes also track other stuff, including the precise location of the seedling's height, whether or not it was planted next to a shade object and what that shade object was. So like a log, a stump, a snag, a shrub, that kind of stuff. And really there's a lot of other things that they do track, but that they don't report, upward into facts. So next slide. So what I'm going to do today is I'm going to just hit some high points of 3 papers that I've been a part of recently that are leveraging this Forest Service plantation monitoring data to explore questions about how a wide range of environmental and operational factors affect the success of seedlings planted in burns. So next slide. The first study that I'll touch on was led by Laura Marshall. And for this work, we used data that we acquired from a national forest, which was the Roosevelt National Forest in Colorado. And then we augmented that with data that we went out and collected in the unit ourselves. So what the Roosevelt National Forest did is they planted 1 unit following a fire with limber pine, ponderosa pine, and Douglas fir. They installed 30 stake rows that captured 300 seedlings collectively, and then they monitored survival after 1 and 3 growing seasons. We went back out into the unit after 4 growing seasons, and we monitored survival again, as well as height and height growth. While we were out there, we also recorded the aspect of the seedling, whether or not that seedling was situated next to a shade object, and then whether or not that seedling was situated in some sort of like localized depression that would allow water to collect around it. And what we found is that survival after 4 growing seasons was markedly greater on north aspects than south. It was also greater for seedlings that were planted in those microsites near shade objects. And it was also greater for seedlings that were planted in those microtopographic depressions. Next slide. So the second study that I'll touch on was also led by Laura Marshall. And for this work, what we did is we only used data that we obtained from national forests. Specifically, we reached out to 4 national forests in Colorado, and we got a bunch of data. Collectively, these data capture 141 units that were planted after fire in 9 different wildfires. And they were planted either with ponderosa pine or with a mixture of ponderosa pine and Douglas fir. Then the forest established stake rows or plots that collectively captured 5,500 seedlings, and survival was monitored after 1 growing season, or at least that's what we focused our analyses on. There was also a fair bit of data that was collected after 3 growing seasons and a little bit that was collected after 5 growing seasons. And so the next thing that we did is we quantified 11 predictors that reflect a range of environmental and operational factors at the stake row or at the plot level. And we were able to do this at this level because we did acquire information about where those stake rows and plots were located within the unit. And what we found is that after 1 growing season, survival was greatest for seedlings that were located on sites where climatic water deficit on average was low. So these are basically your cooler, wetter sites. It was greater for ponderosa pine seedlings than for Douglas fir seedlings. And it was greater for seedlings that were located in sites where the seed lot was basically, quote, moved uphill. So in Colorado, these are operational data. These are locally collected seed lots, and they're moving them within their operational limits. And so you can see in Figure C, we're talking about basically movement of plus or minus 300 meters or plus or minus, 1,000 feet. But even as they're doing things operationally over the last few years or decades, we saw a meaningful effect of this sort of movement on survival. So next slide. So the third and final study I'm going to highlight was one that was led by Kyle Rodman, and he presented a little bit earlier today. For this work, we used data that were obtained from FACTS. And we got these data from FACTS, which is the Forest Service database, by working with the regional silviculturists in regions 1 through 4, which we're collectively referring to as the Interior West. And so what these Interior West National Forests did collectively is they planted 1,100 units after fire. They were distributed across 161 wildfires, and they were planted with a wide range of species. The forest then established stake rows or plots that collectively captured 69,000 seedlings, and they were monitored for survival. Again, our focus is on 1 growing season, but they were also often monitored after 3 and sometimes after 5. So we quantified a range of predictors that reflected a variety of environmental and operational factors, and we did this at the unit centroid level. And we found, as before, that survival was greatest after 1 growing season on those sites where climatic water deficit on average was lower. So these, again, are the cool, wet sites. We found that was greater in units that were planted in the spring versus in the fall. And we found that it was greater in sites where the post-fire planting climate, or specifically climate water deficit, was below average. So basically, in those months following planting, during the monitoring period, climatic water deficit was, cooler, wetter. It was a cooler, wetter condition than normal. So next slide. Thanks, Kyle. So some key things that we've learned is that this data set that the Forest Service collects and maintains has the potential, I think, to provide really valuable insights into what influences the survival of seedlings. We looked at just a handful of factors. I think there are more things that we can look at. In particular, I think it'd be interesting to look even more at some of the operational factors, because these are the levers that we can pull on to help overcome some of the environmental limitations. And so next slide, the last slide, is just, basically this is the tool that I would love to see. If I were a tool builder, I would build a tool that predicts the survival of planted seedlings from both environmental and operational factors. And again, I think that these data could feed into that sort of tool. So next slide. I just want to end on a thanks. These are the folks who've helped us track down some of these data.
Thanks, Paula. I think you get lots of kudos for running through that quickly and still in an informative way. So thank you. I appreciate it. If you're okay with holding questions for a little bit for Paula, I think we should probably move on since we did have a little bit of technical issues. So thank you, Paula. We'll come back around, and hopefully there's also some good discussion going in the chat. I've seen a few pieces come through on that. So, all right. Next, we have Maren Chambers, who's going to be speaking to us about preliminary lessons learned from a seedling planting study in the 2020 Cameron Peak Fire, Colorado. So Maren, it's all yours.
Awesome. Well, thanks so much for the invite to talk with you all about this pilot study that we've been working on. I work for the Colorado Forest Restoration Institute that's based out of Colorado State University, and Kyle Rodman earlier this morning mentioned our collective institutes, so the Ecological Restoration Institute out of NAU and the New Mexico Forest and Watershed Restoration Institute at New Mexico Highlands University are collectively known as the Southwest Ecological Restoration Institutes. We are federally authorized and appropriated in large part And a lot of our mission is really to focus on issues relating to wildfire and forest health, but also really to be a bridge between science and management. So next slide here. So this pilot study that we worked on and are currently still working on it and going to be expanding was really born out of a lot of conversations with managers following the 2020 Colorado and Wyoming wildfire years, which here we saw in that year, multiple fires eclipsed the largest known wildfire that had previously been known in Colorado, which was the 2002 Hayman fire. So as managers were, thinking about doing reforestation as these wildfires were finally starting to burn out, they were asking a lot of questions of folks like myself and a lot of other colleagues who, some of whom are on this call, around things like some big knowledge gaps that they had, which included, if we plant species in the same location as they originated from, will they be successful into the future, particularly thinking about changes in climate and in disturbances? And if we utilize climate-informed reforestation actions, like, for example, moving species uphill or up in elevation, what kind of climate sensitivities might we be seeing, and will they survive and be resilient? So these had been questions that I had been, connecting with a lot of managers here in Colorado for quite a while. And in 2020, when one of my Arapahoe Roosevelt National Forest colleagues was ordering seedlings, he actually decided to donate seedlings to us for a pilot study to sort of get to some of these questions. So our study goal was really to understand planted seedling survival and growth and mortality dynamics following winter and summer seasons of this sort of interesting study design. So we planted seedlings in the 2020 Cameron Peak fire, which is now Colorado's largest known wildfire, which burned over 200,000 acres in northern Colorado. And this fire burned across multiple forest types and a very broad range of elevations, including ponderosa pine, mixed conifer, lodgepole pine, and subalpine fir. So we took that landscape and we planted all of the seedlings that were donated to us by the U.S. Forest Service that they were planting in some of their original planned reforestation actions following the 2020 wildfires. And so this included ponderosa pine that was sourced from two different elevational sources, around 8,000 feet and then also around 9,000 feet. Also Douglas fir, limber pine, lodgepole pine, and Engelmann spruce. Next slide, please. And so in our plots, we planted all of these seedlings in a randomized design at previously established plots where we had been monitoring understory vegetation and tree recovery and fuels dynamics post-fire. And so we planted ponderosa pine and we planted every single one of these species in every single one of our plots across that broad range of elevations. And we planted these seedlings in spring of 2022. And then we monitored these seedlings post-summer in the fall and then also post-winter in the spring. And we've done this all the way actually through 2024, but I was only asked recently to present on this work. So I'm going to be presenting data from our 2023 data set, as we have yet to actually analyze our 2024 data set. But I do want to mention that in spring of 2023, we were not able to do monitoring in our subalpine forest type plots due to persistent snowpack that lasted through the summer. Next slide, please. So some preliminary lessons that we're seeing from this, pilot study is that, the vast majority of our seedlings did survive by fall of 2023. However, we were seeing that our lower elevation sites, so this is in our ponderosa pine dominated forests, had our lowest survival rates. And this was a significant result. And that our highest elevation species had the lowest survival at these sites. So that included Engelmann spruce. So this kind of makes sense, right? We would anticipate that our highest elevation species are not going to do very well at our lowest elevation sites. But what we did see that was interesting is that at least preliminarily, our higher elevation sites are showing a trend of higher survival rates for all species, including our lower elevation species, such as ponderosa pine. And so we are seeing that seedlings are surviving outside of their forest type of origin. Next slide, please. And we also wanted to look at preliminarily kind of what was going on between winter and summer survival because of these big questions around kind of cold and drought tolerances. So we did see that a little under 20% of our planted seedlings had died due to what we're calling winter or summer season stress. And this was particularly so in our ponderosa pine dominated forest plots, where average mortality was much higher than in winter than in summer. And that was also a significant result. And we saw that mortality was highest for Engelmann spruce and Douglas fir. And again, we saw this trend of higher mortality for all forest types following winter than in summer. Next slide, please. So our next steps are that we've been funded by an AFRI grant to expand this study to 2 additional fires that have burned in 2020 and 2025. We will be adding pinon pine to the suite of species that we'll be planting in this study. The reasoning for that is that the northernmost stand of pinon pine is actually in northern Colorado, only about 15 miles or so from where I'm sitting right now, and is a few dozen miles from the majority of the wildfire perimeters where we'll be planting these seedlings. All of our species that we'll be expanding will also be sourced from 2 elevations, and we'll be monitoring this long term, asking a lot of additional questions and sharing results widely. Next slide, please. And so what we've learned from this preliminary study, this pilot study, is that seedlings are surviving outside of their forest type of origin, at least in this first few years. And this is especially so at higher elevations. But what we're also seeing is that while summer stress, such as drought or heat, is important, winter stress, including cold or snow, may actually be more important. And so this may be due to winter, like minimum or maximum temperatures, or winter precipitation or the lack thereof. So I think for development of a comprehensive reforestation tool, including some of this seasonal data, including temperature and particularly winter precipitation, will probably be really important to understand some of these kind of localized findings. And in addition, in the Southwest, we have very few common garden or planting studies. And so this was part of the initiation of this study. But incorporating findings from any kind of these studies where are appropriate could be really helpful to inform some of the local nuances that we have already been talking about throughout this, this summit today. Next slide, please. And finally, I think just a huge thing to incorporate is monitoring, both as a tool that we can include monitoring in, but including monitoring data into a reforestation will greatly benefit reforestations because of these local nuances that I think that we continue to learn about through all kinds of different reforestation efforts. So there's a lot of people to acknowledge for this. I'm just going to end here. I have to give a huge thanks to our CSU field technicians, the Arapahoe Roosevelt Pawnee National Forest, and funding from AFRI, as well as the Southwest Forest Health and Wildfire Prevention Act. So I do have to leave in about 20 minutes for a little while for a meeting. So if I miss any questions later, my apologies, but I'm happy to answer any now in the chat or later, and my email address is right here. So thank you so much.
Thanks, Maren. Appreciate it. We will pause for questions unless I'm hesitant to catch any more right now since we are running a little bit behind. So if it works, if those folks who do have virtual questions for Paula and Maren can drop them in the chat, and we will circle back to questions in the room moving forward. So thank you. All right. Up next, we've got Alap Dixit, who is going to be talking to us about assessing combinations of nucleation size and planting density to improve survival and performance of planted ponderosa seedlings. So all yours.
All right, thank you. Good afternoon, everyone, and thanks for having me here. My name is Alap, and I'm a faculty at Oklahoma State University. Today, I'll be sharing some early results from our work in northern New Mexico. So the focus of this talk will be on the planting stage of the reforestation pipeline, especially looking at impacts of combinations of nucleation size and planting densities on performance of ponderosa pine seedlings. Next slide, please. Can you just press next a couple times, please? Some animation there, yeah. All right, so the study site is Philmont Scout Ranch in northern New Mexico within the Youth Park fire burn scar that happened in 2018. So 3 years after the fire, about 8,000 seedlings were planted in October of 2021 in a randomized complete block design with 2 nucleation sites or tree islands and 4 planting densities. For the seed folks here, seeds for this study were collected from sites in northern New Mexico with climates and elevations similar to the field planting site. So from about 2,500 meters. Next slide, please. I think that's good, yeah. More on the treatments here. We use 2 nucleation sizes, so 1/2 acre and 1/8 of an acre, and 4 level of planting densities. Next, please, just one. So it's one more. Next. Sorry, I didn't realize I wouldn't have the control. So it's 194 trees per acre, which is the lower end of the spectrum. 436 trees per acre, next, which is our 10 by 10 feet spacing. 889 trees per acre and 1742 trees per acre is our higher end. This results in 8 different treatment combinations, with each treatment combination replicated in each of our 4 blocks. So we specifically added some of the very higher densities to cover that end of the spectrum. Anyway, so before planting, all plots went through wedge control using brush saws. And at the time of planting, each seedling was enclosed with a photodegradable Vexar tube for protection against herbivores. We also installed climatic sensors at the plot center and also inside and outside in each cardinal direction to monitor, relative humidity, temperature, and things like that. Now, with treatments like nucleation size and densities, it's important to know that it's really a longer time study, and we don't expect to start seeing some of the treatment effects for another several years. But I'll share some of the early results here. Next slide, please. One more. Yep, there you go. Here we go. So survival after 3 years of planting. Remember, planting was in 2021. So 3 years after that, as of fall 2024, survival is about 80%, which is much better than what has been reported in the Western United States, right? Yeah, there you go. Multiple studies in the Western US has reported, we hear this figure of 25 to 35% survival. So 80% is pretty exciting. As expected, not much treatment differences this early in the project. As I mentioned, we'll wait for another decade or so. Next slide. Now, the main source of mortality here was herbivory by ungulates mainly and rodents. The figure shows plot level herbivory versus percent of Vexar tubes or tree shelters that are still intact in the plot. As we can see, a strong negative relationship between the 2 variables. It's important to note that we lost a lot of our Vexar tubes early on due to winds and snags falling and trampling by animals and things like that. Next slide. Again, as expected, herbivory is not only impacting survival, but also growth. Again, a strong negative relationship between the variables. Next slide, please. So in summary, as this group here already knows, that large-scale reforestation is challenging and resource-intensive. But with such a high backlog, perhaps we can leverage things like nucleation planting, which is more resource efficient and closely mimics ponderosa's natural region, especially in that area. And lastly, and most importantly, the result emphasizes yet again the importance of considering impacts of herbivores while planting large-scale reforestation of ponderosa pine. Next slide, please. So in terms of, one thing to emphasize or think about, ideally, I think incorporating and accounting for herbivory-related mortality in the planning process would be great. I've experienced these issues in all of the projects that I've worked on in Region 3. This is actually not as much mortality in this particular project. In most, I've seen 80–90% mortality because of ungulates or rodents. The picture on the right is from another project, from one of the common garden studies in Arizona that we set up in 2018. What happened here was we fenced the whole project area with the hope of avoiding herbivore-related mortality. But the use of fencing to prevent ungulate herbivory may have indirectly increased herbivory by small mammals within the fenced area, right? Because of because we excluded predators or mesocarnivores from the fenced area as well, right? This caused a loss of about 10% of seedlings every week until we made some makeshift chicken wire tree shelters, which stopped this feeding frenzy. So I don't think that this herbivory piece of it gets talked about enough while thinking about large-scale reforestation. So we need to explore durable, effective, and economic alternatives for these shelters, and they'll be crucial to improve survival rates. We would not want to lose our investment in rest of the pipeline. We talk about appropriate genetics, nursery stock type, stock size, planting techniques, and more. But if we lose most of our planted seedlings to herbivory, that's something to think about. So all in all, by optimizing techniques, spacing, and ensuring effective protection against herbivores, we can improve the success of our reforestation projects in post-fire sites in the southwestern United States. Next slide, please. And lastly, I want to thank all these amazing people who made this project possible. So thank you.
Thanks, Alap, and thanks for dealing with my slide advancing skills or lack thereof. I appreciate the flexibility there. I think we do have time. Oh, great, thanks. I think we do have time for one question if there's any in the chat or in the room for Alap. Great. Thank you, Alap.
I'll shoot real quick. A lot. So I'm just trying to figure out how to deal with your herbivory problem, and would actually using fencing instead of kind of single wrappings be more efficient? Is it more efficient for some species versus others? So have you looked at more of like that larger scale fencing strategy?
Yeah, so that's a good question. We are still figuring that out, right? So we have an active study that's looking at all combinations of shelters and fencing. So no protection, just shelter, just fence, and a combination of shelter versus fencing, right? So we're still analyzing that data, looking at what's the best combination. But it's important to remember that when we are using fences, we are also excluding the mesocarnivores, right? So within the fence, the rodent population can shoot up, which would cause a lot of damage really fast. Something to think about.
Thank you. All right, I see one other hand up virtually. Tom, do you want to ask that really quickly? If it's a quick one, if it's a long one, I might ask that you put it in the chat.
It's quick. Did you find any provenances that were resistant to herbivores? I think that's pretty common.
Yeah, so in the common garden study, we did not see a provenance effect on herbivory. It was mainly on the edges, right? So all the animals would start coming from all the edges and work their way towards the center. So nothing yet in Ponderosa pine.
Awesome. Thank you. Appreciate it. Circle back to more questions a little bit later. All right. Last but not least, in the seedling survival and monitoring, although I feel like all of these kind of different sections could be rolled into one at this point, we have Carlos, and I'm going to botch her last name, so I apologize, Carlos, but Beneke, is that anywhere close? Who's going to be talking a little bit? Very close? Okay, good.
Okay,
So,
thank you, Rob. Well, my name is Carlos Gonzalez. Beneke is my mother's last name, so
okay.
Thank you. Anyways, I'm a faculty at Oregon State University. I am the director of the Vegetation Management Research Cooperative. And we've been developing since 2016 a project that we call CoSign, Competition by Sign Interaction Experiments. We are addressing and trying to understand the mechanisms of competition and trying to incorporate the competition with the early seed vegetation and the planted crop trees, develop models and a decision support system. So today we'll present you our efforts in terms of modeling drought-induced mortality, where we use climate, soil, and the physiology of the seedling. Next, please. Okay, so this is the project, the cosine experiment. We have a network of 14 sites from Seattle to South Oregon. It's basically a 2x2x2 factorial design. It's basically combinations of herbicide treatment from pre-planting and to post-planting, yes or no, yes or no. And that created the variability in conditions of vegetation abundance and diversity. In that picture, we have examples of 4 of these treatments, okay? So, and that changed the composition and the abundance. That is very important. So we have for the same site and the same climate, you have differences on that. Can you please move? Next. So on each side, we have a weather station where we're monitoring the weather variables, and we have monthly clip plot measurements, so we can address the cover and the height and the biomass development of vegetation. Once a year, we do a seedling biomass, also with nutrients and all the stuff. And every month, this is from April to October, we measure the physiology of the seedlings as well, so the water stress, because this is focused on water stress. We have soil moisture sensors, 2 per plot. This is a large data set, and we also, once a year, at the end of the summer, we do hydraulic conductivity sampling on our seedling. The same seedling that we do biomass, we also measure hydraulic conductivity and vulnerability to cavitation. Next. So I will be very fast. I will summarizing 7 years of research in 7 minutes. So at the left, we have a figure where we can model the dynamics of early seed vegetation, cover, height, and biomass, just using climate and soil. Okay? So you can see in the figure at the left, we have 3 sites, one wet site, intermediate, and dry and intermediate site. And the different colors are different type of vegetation. We group the vegetation. We cannot do this for each species, but we can group them by shrubs, graminoids, forbs, ferns, etc. And the black is the total. So as you can see, the figures shift, the curves shift and adapt to the climatic conditions. So each vegetation depends on more like the rainfall in May or different combinations of environmental variables, and that changes the abundance and the dynamics of that vegetation. Using our soil moisture sensor, we are able to simulate water use of that vegetation, and hence we can simulate the soil moisture. So the figure at the center shows the soil moisture predictions. So on top is the observed. The different colors are different treatments. So the red and black are with a less intense vegetation management, so the soil moisture drops more. And we have different models to do that depending on the data availability of the user. So if we use vegetation type data, so include ferns, forbs, graminoids, etc., cover, we can predict it in a much better way. So at the right on top, we have, using those changes in soil moisture, we can predict the pre-down water potential. That is very well known, but what is most important, we can predict the midday water potential. So we have 1,600 plot level data, and multiply that by 3 or 4, that is the number of samplings per plot of data between that we measure pre-down at 5 in the morning, midday at noon, and also we have weather data. So we can predict the midday water potential. Next. And at the left, we have this vulnerability to cavitation curve. So this is the drought resistant index. At the top left, we have this vulnerability to cavitation curves for Douglas fir and Western hemlock. So, and it's the relationship between the percent loss of hydraulic conductivity with the pressure applied. That is the same as the tension inside the xylem of the seedling. Okay, so they are different, the 2 species. What was most important is we collected seedlings at year 1, 2, or 3 after planting. And we then overlap those measurements with the measurements that we did at the greenhouse stage, at the laboratory. So we have in situ and laboratory measurements on the left bottom figure. So the dashed lines are the same lines on top. And the symbols represent the mean value because we didn't find differences between year 1, 2, or 3. on those. So they overlap. So that it demonstrates that the theory, these laboratory measurements, match with the field observations. On the same plots, we have observations of mortality during the growing season. Every month, we are seeing if the seedlings were dying, in addition to the growth. And what we observed is that we found that those curves that goes up at the center represent the relationship between the percent loss of hydraulic conductivity, so it's the amount of cavitation inside the xylem, with the mortality. So when they have 50% loss of hydraulic conductivity, zero mortality. But when they reach between 85 to 90%, there is 50% mortality. So with those curves, if we link together with the vulnerability to cavitation curves at the left, we can simulate mortality based on the midday water potential. And those are the curves at the right. So the curve on top is the vulnerability to cavitation curve using the midday water potential as our explanatory variable. We link that with those mortality relationship, and we finally have this mortality curve. So you can see at the figure at the bottom right, with 1.5 megapascals of tension, zero mortality. Simply know that, okay? That is the permanent wilting point for sunflowers. Sunflower wilts. Trees don't care about that. But if you observe at, like, let's say at 2.5 megapascals, Douglas fir, we have about 20% mortality, while Western hemlock, we have more than 60% mortality. And that is the relationship, that is our magic relationship that we can now, if we have geographic data, we can produce maps for predicting mortality. Next. So what we know that we can predict early setup vegetation dynamics, cover height and biomass based on weather and soil. Then we can predict the changes in soil moisture because we know the water use of that vegetation. We can predict pre-dawn water potential, midday water potential, then the impact of that and percent loss of hydraulic conductivity. And then we incorporate the genotype specific families or species, this vulnerability to cavitation indexes. And then we can predict the percent loss of hydraulic conductivity for that particular genotype, and then we can predict mortality. At the final slide. So we are working now on developing maps and a system that will estimate. My dream is having like a phone application. So using the location and the coordinates or the unit where you are, based on some assumptions, I can do or not with control. I will use this species or this family. And the climate, well, we will put some scenarios. This year will be El Niño or La Niña, dry or wet or just average. And we can predict an estimated probability of mortality. The figure, those are those maps that represent the percent loss of hydraulic conductivity based on some assumptions. So where the species, that Greek letter psi 50, that is the drought resistant index, is the same, but the pre-dawn water potential, so at the end is the soil moisture, and the one at the right is 1.5, negative 1.5 is dry, and the other is negative 0.7 is wet, more or less wet, and you can produce those different kind of maps. And the figure at the right is what we are working right now, is expanding all these physiological measurements to 55 families of Douglas fir, including eastern, interior, and coastal Douglas fir, and some hybrids. The same procedure can be done for any species. Okay, I think that is my last slide. If we go to the next. Just, I'm very sorry that I didn't say thank you, but I want to thank the organizers of this meeting. I'm very sorry that I was unable to go there. I'm in a search committee. We're looking for a new faculty, so I was able to be here with you. I'm very happy of being with you guys. So if I can be of any help, I'll be happy. And also, all this area of the developing the system, if people more smart than me can help us in order to develop that decision support tool, we'll be more than happy. But we are working on that. We are using 800 by 100 meter grid of climate from the PRISM project. That's it. Thank you.
Thank you, Carlos. We're lucky to have folks at Planscape who actually know how to build all of these things. So great. But Carlos, we're going to keep pushing on to the next section. We'll keep eyes peeled for questions in the chat.
Yeah, I'm very sorry. I had to leave to continue with the interviews.
Great. Good luck with that. I hope it goes well.
Thank you.
Appreciate you.
Thank you. Good luck.
All right.